me organizing this paper. It's also very lucky to present my dissertation paper in this conference. Okay, great. So today my topic is data-driven resistant robust regression. So imagine, imagine you have a data site. That's the situation you met, that most of the data site located at the bottom. However, there's one outlier, which is 1 equals to 40. So ask yourself, what are you going to do? There's two options actually. One is that you can just remove this outlier by hands and tell yourself that it's okay to run the regression or anything. But the other case, like you just want to use one regression method, pretending that this method can help you to find the optimal result. However, in my mind, I would consider about the second option just to do more research about that. That's the reason I organized this paper. So before going into the details, let's say what will happen if you just use methods to this kind of data science. So first, let's zoom in, say that the data is around the range from -1 to 4. So assume we know the true function, which is the right line. And let's say the effect of the linear regression, which is the black line. We can see that the outlier drove up the linear regression result a little bit up, which is biased. And we can also apply non-parametric methods to this data size. And as we all know that for non-parametric methods, the bandwidth selection is very important. So here we show 3 non-parametric results according to different bandwidths. So among these 3 results, we see that the purple line is the worst situation, which is drove up by the outliers a lot. And however, for the purple line and the pink line, before knowing the true function is the right line, it's hard for us to distinguish the property of these 2 lines. And that means it's hard for us to say which one works better for us. So because of that, or given on this fact, my research focused on when we face this kind of like a contaminated data site, how to figure out a robust function in the non-parametric field. As we all know that basically in the non-parametric field, bandwidth is a key factor. So you can also think my paper mainly works on finding the optimal bandwidth. And this is the literatures I go through when preparing for this paper. Basically, this is 2 parts. The first part is from 1964, Huber, to 1999. All this paper here just to talk about the general properties about non-parametric methods and also the property of the outliers. And the second part is Leon 2005. Actually, my paper is based on this paper, based on Leon 2005, and also my general propositions is just some result of adjusting Leon 2005. So let's go to the model. So my basic model, or my Bayesian model, is quite simple. Assume that you have a data site. Y is the dependent variable, and X is the independent variable. The M here is the unknown function. So the general process to find the bandwidth is to use the leave one out method. So the first step is indicated by the equation 2. That is, we use the non-parametric kernel function, which is K here, and also a square function. By equation 2, we get the estimator M hat. And by bringing this M hat to the leave one out cross validation process, we have the selected bandwidth. How to get it? We just minimize the CV, then we get the bandwidth. So it's quite obvious that in the equation 2 and in the equation 3, we only use the square function. So if you still remember the data side we just showed before, assume like you have a value which is 40, then we can see that 40 squared will be 1600. So that special number, a special data point will make this equation 2 result quite biased. So if you bring this biased estimator and head to the to the equation 3, it's quite easy to think that this the bandwidth we got in this equation 3 is not optimal one. So that's the main reason why we think it's very necessary to introduce the robust function instead of just use the square function here. So because of that, we rewrite the equation 2 and 3 by 4 and 5. In the equation 4, we write the rho SM stands for the robust function in the smoothing process, and the rho SL stands for the robust function in the selection process. So maybe some of you not familiar what the robust function means. So here I just show one specific example and give you guys some general impression. So the most, in my mind, the most common used robust function is the Hilbert function. As the equation 6 showed, there's 2 variables in this function. You can treat the variable c as the threshold. Okay, so when the absolute value of u is smaller than c, then the robust function just perform like the square function, like a rho u equals to u squared. And when the absolute value of u large or equal to the threshold, then the robust function is linearly related to the absolute function of the u. And perhaps one plot will help you get impression why we think the robust function works. So this blue line here stands for the square function, correct? And the brown one here is the Hilbert function. If we just look at the range inside -2 to 2, we see that between the Hilbert function and the square function, their difference is just tiny, right? And however, if you look outside this range, for example, if you look at the point when x equals to -4, then the square function result will be 16. However, for the Hilbert function, that would just be 6. So the gap between these two functions is already 10. So it's easy to say what's going to happen if the x goes to something like 40, 100. So this plot, in my mind, just to tell you the function of this Hilbert, as a Hilbert robust function and why we think it works for us. Okay, by understanding these details, then we rewrite the cross-validation equation CV as the equation 7 shows, which is RCRVD. We see that the variable we still want to find is the optimal bandwidth age, and the extra variables is the 2 variables, CSL and CSM. And the main issue of the RCRVD is this 2 variables, CSL and CSM. We see that is decided by the users. That means in order to find this optimal bandwidth age, you have to cite these 2 variables by yourself. And actually, this is also the general conclusion from Leon's methods. In Leon's in Leon 2005, he just used RCRVD to find the optimal method age. However, because the purpose of my research is to find one data-driven robust method, that means we would like the data set itself to tell us all the variables. So it's quite necessary to think why CSL or CSM works for us if we set them at 3. Or maybe there's other situation that is a random chosen CSM, CSL does not change the general performance of RCRVD. And this kind of like an issue, if we map this kind of issue to the reality, it's kind of like you want to buy a self-driving car. And what you imagine is that you could read a book or watch a video or even play a game during the driving. However, the reality is um, on the driving, you have to watch the car drive, even though you don't need to hold the wheel. So this kind of this definition kind of contradicts our imagine of self-driving car. So this exactly same to the situation we met. We want to have a totally data-driven robust method. However, the RCRVD forces you to choose two variables before applying these methods. So that's not what we want. But before going to the details, we also want to see whether random choosing CSM and CSL works well for us. This is 3 dimensions plus tell us the details. So the X and Y planes is the bandwidth H and the threshold C, and the Z-axis is the RCRVD. So you can see that the yellow line stands for the optimal bandwidth, and the right line stands for the optimal C values. We see that the different combos of H and C results in different RCRVD. And at the left corner, we have optimal RCRVD. So this plot just shows you that different combos of H and C results in different RCRVDs. So based on that, we thought it's quite necessary to free these two variables H and C. I'm sorry, to free all the variables related to C and find all the variables at the same time. And that's the reason we propose our statement, which is a little bit different from the Young 2005 because we free the two variables CSM and CSL. And the next question is why we think equation 8 works for us, or is there any issues involved in freeing these two variables? So we open this equation DRCV in these 3 parts. So in the proposition 1, there's some condition A1 to A8 because of the lifetime limit. We didn't discuss the details. Actually, A1 and A8, they are just general assumptions for non-parametric methods. And there's also one event P, which is related to the second derivatives of the robust function. So here we just skip the details. We just look at the general formula of the DDRCV. We see that there's 3 parts in this term. The first part is the expectation of the robust function in the selection process. The second part is one exterm expectation times the MLC. The third one is the remaining. So the reason why we think the DDRCV works for us is because when you minimize the DDRCV, what you want is to get a minimized MASE. MASE here is the mean average square error terms. So a minimized MASE means the estimate work for us. However, sometimes this situation doesn't satisfy the purpose because when you look at the details of the psi definition, which is indicated by the equation 9, that is, if the absolute value of U smaller than C, then the psi will just equal to 1. However, when the absolute value larger or equal to C, then the psi prime will just equal to 0. That means if you allow the data set itself to decide what kind of C it wants, then the data probably will always choose the minimize C, or let the C go to closer to 0. So if by that, if when you minimize DDRCV, you will just get a minimized E expectation of the robust function in the selection process, which is nothing to do with the MASE. So because of that, we thought we propose some like edited propositions based on the general proposition 1. The first option is we set a fixed CSL for the DDR-CV. In that case, for the DDR-CV, we only have two variables. The first one is bandwidth age, and the second one is the threshold in the smoothing process. And the other options is that we replace the Hilbert function by the absolute value function, which is U. And we show in the paper that after some game of math, we will get equation 10 and then 11. In equation 11 and 10, we see that after replacing the Hilbert function in the selection process, we will have the new DDR-CV, which is just related to the age and the CSM. They're nothing to do with the threshold and nothing to do with the CSM. And the equation 11 is the case that we replace both of the Hilbert functions in the smoothing process and the selection process. In that case, we only have absolute value function works for us as the robust function. As the equation showed, there's nothing to do with the variable CSL. And F0 here is the general density in the data sites around the general density of error terms around the point 0. So, even without the details, it's easier for us to understand that the method 11 works faster than us because you don't have to pick up the extra variables. However, it's very important for us to realize or to compare what's the performance of these three methods. So so generally until here, we already talked about the main propositions in my paper, and the next parts we show that first of all, how the robust function perform better than the LSCV methods, which is just a method just to use the square function. The second part is we want to compare the performance among these three robust functions, and we name the function only use Hilbert robust function as the general E function, and we name the other two as ABS, ABB. ABS, it means you use Hilbert function in the smoothing process and absolute function in the selection process. And ABB means that you only use absolute value function in the process. So this table shows us how a general E function perform better than the LSCV. So the DGP is the function y equals to sine 2 pi x plus the error term, which is the IID, normal distribution. And in the data size, we assume the contamination distribution is Cauchy distribution. So 0% means all the error terms from the normal distribution, and 40% means that 40% of the error terms from the Cauchy distribution. And all the numbers here stand for the ratio between the robust function and the LSCV. This all numbers about the ratio of MSE. That means when this number larger than 1, then the robust function perform worse than the general LSCV methods. When this number is smaller than 1, then we think the robust function perform better. So when we look at the case when all the error terms come from normal distribution or your data is perfect, you see that no matter in what kind of sample size, the performance of the LSCE is better. That's the reason generally in the regression world, when you believe your data is perfect, you can just use the general non-parametric method. And however, look at the case when it is 40% contaminated. In this case, the ratio almost close to 0.2 when the sample size is 100. So that's the reason we think the robust function works really well for us. And the next part is the comparisons between these three proposed methods. As we mentioned before, the first method is about DDRCV related to the Hilbert function, which is applied in the smoothing process by selecting a fixed C for the selecting process. And the next ABS, ABB just related to the absolute value function. And so this is the first case. This table show us the comparisons. So we cite ABS method as the base method. We want to say, so this column stands for the comparisons between general E method and ABS. This column stands for the ABB to the ABS method. So here the mixed number 100% means for example, for this column, that means 100%, that means your contamination only from one single outlier distribution. That means for this column, all the results from the combination of normal distribution and the Cauchy distribution. And all the numbers here stand for the ratios of MASE. So we see that in this columns, the performance of general E and ABS, they are close to each other. And in this ABB to ABS, we see that this ratio is larger than 1. That means the ABS method performs worse than the ABS. And for the Laplace and logistic, it's the same thing. And generally, we see that in the 100% mixed situation, ABS perform better than ABB, and ABS perform closer to the general method E. And remember that because when we set these experiments, we already know the perfect perfect number for CMX, which is equal to 0.5. That means if the method ABS perform closer to the general method E, then we think ABS should be our choosing method. We also provide a second case. That means your outlier comes from a mixed situation. That means your outlier, half of your outlier from Cauchy distribution and half of outliers come from Laplace. This row stands for. And another situation is like this case, like half come from Cauchy distribution and half from the logistic distribution. And in this half and half mixed situation, we see that only one case, that's the ABS, perform worse than the ABB, and for the rest of two, it's the same case like the 100%. And also the ABS perform closer to the general E. And we also provide some extra case that is not half and half mixed. This is same thing to the previous situations. That means 70% of the outlier comes from Cauchy and 30% of outlier comes from Laplace. Then we discuss the result. And in this table, we also see that same thing, that ABS method perform better than the ABB, and the ABS method perform closer to the general method E. And so based on this table, we thought that if you have contaminated data sites, it's better for you to use the method ABS, since generally it's hard for you to get a perfect threshold variable C fixed. So if you know nothing about that variable, it's better for you just to apply the ABS method directly to your data site. And also, as we mentioned before, since ABB method does not consider any related variables, consider any variables to the Hilbert function. So if you have a really large data site and also you want to get a faster result, you can use method ABB. And this next table show us or give you a general impression how a robust function can help you to improve the performance of the LSCV. So we see that suppose you have a case that 7% of the error term from the normal distribution, the sigma equal to 0.5, and the 30% of your outlier comes from the Cauchy distribution. So we see that when the sigma from the Cauchy equals to the 0.5, which is same to the normal distribution standard deviation, then the performance between the LSCV and the robust function, they are exactly same. However, when the sigma increase from 0.5 to 3, we see that the robust function almost improve 7 times of the performance of your LSCV. So so this table generally give you an impression what's the expected result you would have if you want to use the robust function. For example, if you think your data is media contaminated, maybe you will expect 2 or 3 times better result than the LSCV. If you data is highly contaminated, maybe you will expect much better performance from the robust